All right, if we take a look at example number 7, we are given that we have a capacitor with a value of 25 nanofarads. We're also given that the distance between the plates is 0.15 millimeters. And we're given that the charge on one of the plates is 0.20 microcoulombs. First thing I want to do is put these into a form that is going to be usable by me, and by usable I mean something that I can actually punch into a calculator and get real answers out of. So this needs to be in farads, that's going to need to be in meters, and then my charge is going to need to be in coulombs. So 25 nanofarads is equal to 25 times 10 to the negative 9th farads. 0.15 millimeters is 0.15 times 10 to the negative 3rd meters. And then 20 microcoulombs, or 0.20 microcoulombs, is equal to 0.20 times 10 to the negative 6th coulombs. All right. Part A says we want to know the area of each plate. So what we're going to do is say A, the area, is what we are looking for. The equation we're going to use is C is equal to epsilon naught times A divided by the distance in between the two plates. What we are going to go ahead and plug in is, well, the reason we use this equation is because we have capacitance. We are not given sigma naught in this, but we know that the permittivity is 8.85 times 10 to the negative 12th, blah, blah, blah. So we're going to plug that in here because that's always what that is. And then we are looking for the area, and we have the distance. So I'm going to go ahead and solve this in terms of the area because that's what we're looking for. So you know that the area is equal to the capacitance times the distance between the plates of the capacitor and divided by sigma naught. All right. So our next step is going to be to go ahead and plug those values in. So we get equals capacitance is 25 times 10 to the negative 9th farads. All right, the distance between the plates is 0.15 times 10 to the negative 3rd meters. And we're going to divide all of that by the permittivity, and the permittivity is given to us as 8.85 times 10 to the negative 12th newtons, nope, that's coulombs squared per Newton meter squared. We're not squaring any of the actual values. The square is only in the unit. So we're going to go ahead and put this into the calculator, and the answer we get back should be 0.424. It's actually 0.423 something something, but we're going to round it to 0.424 meters squared. Okay. Part B is asking for the electric field between the two plates. So I'm going to go ahead and write that down. B is asking for the E field between the plates. All right. So we know when we look at our equations that the E field for a capacitor is equal to the change in voltage divided by the distance over which that change in voltage is occurring. That's not just for a capacitor, that's for anything. But we're applying this specifically to a capacitor. All right, well, we do not have the change in voltage, but what we do know is that delta V is equal to Q divided by the capacitance. That's the charge over the capacitance. So what we're going to do is combine this and put it in here for that. That's going to give us that our E field value is going to be equal to Q over D times C. All right. We're going to go ahead and plug everything that we know into that. Q is equal to 0.20 times 10 to the negative 6th coulombs. Put that in some parentheses. The distance is 0.15 times 10 to the negative 3rd meters. And the capacitance is 25 times 10 to the negative 9th farads. right? When we put all this into the calculator, we're going to get 53,333. The unit for this is the standard unit for an electric field, and that is newtons per coulomb. Part C is the last thing we're looking at on here. And for part C, we are being asked to find what the potential energy between the two plates is. So what we have to do is say our potential energy is equal to, for a capacitor, 1/2 of Q times delta V. Again, we do not know delta V, but we do know that delta V is equal to Q over C. So we're going to go ahead and plug that in and say equals 1/2 Q times Q over C. That's ugly and imperfect, so we're going to say equals Q squared over 2 times the capacitance. And that's the equation we're going to use to solve this out. So we're going to go ahead and plug everything in there. Q is 0.20 times 10 to the negative 6th coulombs. Be sure and square that. And we are dividing that by 2 times the capacitance. The capacitance is 25 times 10 to the negative 9th farads. If we put that in the calculator, we get, here's 2 times 10 to the negative, or 0.2 times 10 to the negative 6th squared. That matches up. Divided by 2 times 10 to the 25th, I'm sorry, 2 times 25 times 10 to the negative 9th. There we go. When we plug all that in, the value that we get back is 8. It's exactly 8 times 10 to the negative 7th. Potential energy is going to be joules. If you guys follow through with Coulomb squared per farad, that's going to end up being joules.